Hi, my name is Derek Bingham. I'm a developer advocate at AWS, and today I'm going to tell you about 5 design patterns to build resilient apps. Over the next 30 minutes, I'll show you 5 patterns and 1 practice that you can use to build your modern, distributed, cloud-native apps with more resilience and to delight your users. I'm going to start this talk with a quote from our CTO, Dr. Werner Vogels. Failures are a given, and everything will eventually fail over time. Now, when I talk about this quote, the first reaction I see from customers is, oh no, everything's failing. Well, actually, it's the essence that you've got to think about. As modern application builders, we need to think about what components are in our applications and what particular failure modes may happen. For example, our applications may run on different technology stacks. They may run on different servers. They may run across a whole bunch of different networks. And these are all potential failure modes for our application that we must think about and consider when building our application. Because in the end of the day, our users are the most important part of our application. And if they are thrilled and excited by our application, then we will win. So today I'm going to show you 5 patterns and a practice that you can use to really build out your resilient applications and delight those users. We're going to talk about timeouts, graceful degradation, retries, exponential back offs and circuit breakers, and then I'm going to introduce you to a practice of chaos engineering and introduce you to a new AWS service that came out last year called the Fault Injection Simulator. Let's get into it. So let's meet our application that we're going to be building today. It's a distributed microservice 3-tier application. It's built in .NET, and let's go through the application itself. So the front end is a React front end. If I just zoom in here, you'll see that I've got inside the source folder, I've got a fetch data file. The fetch data is my main component. So if I scroll down here, there's nothing much to it. It's got a simple UI that will display some jokes, and it will have a button as well that will show me or ask for another joke. Once you depress the button, it will make a call out to an API, fetching the data, and that response will be serialized back and shown to the user. So the API that it calls is a .NET microservice, and this is a controller here that I'm showing you. And what it does, it invokes a new instance of a client and then goes and grabs a joke. And this is this client itself. So it will then call out to a third-party joke API. It will call that API, expect a response, and then with the response, it will serialize and deserialize into a joke object. And the joke object itself is very, very simple. I'll show you that now. It has 3 bits. It has a setup, a punchline, and a source. So if I run this application, hit F5, you'll see, why are monkeys great at sports? They are born champions. If I hit tell me another, it will retrieve another joke. What is the object-oriented way of becoming wealthy? Inheritance. And tell me another, retrieve another one. How many programmers does it take to change a light bulb? None. It's a hardware problem. If I look behind the front end, you'll see that this is showing me the JSON that's being returned. And again, we've got our setup, punchline, and our source. I'll talk more about the source throughout this talk. At the minute, the source can only be the third-party API. So that's our application code. How does it work architecturally? My React web application calls the .NET microservice. The .NET microservice proxies it to a third-party joke API. The third-party joke API returns a joke. The .NET microservice then proxies that back to the client. But what happens if the third-party joke API runs into problems? So during this talk today, I'm going to simulate that by getting the third-party joke API to respond to all requests after a random number of seconds. So if a client hits my .NET microservice and my .NET microservice proxies, it could be waiting for an indeterminate amount of time, which could then makes that my React web application could also be waiting for an indeterminate amount of time. So another React web application could possibly make another request, which my .NET microservice would proxy, and that request would wait as well. And then that pattern could be repeated until my .NET microservice itself is overloaded, as all these requests come through and they're all waiting. So ultimately, my client and all my clients, none of them will work. So let's see how we can address those situations. And let's look at our first pattern, which is timeouts. So here I am in my .NET microservice. I'm going to use a third-party, for this one, I'm going to just simply add a timeout. So to add a timeout in a .NET HTTP client call, you simply add a property called timeout, funny enough. So I'm going to set this timeout to be 5 seconds. Let's select this time span. 0 is not going to work. So let's remove that and give it a actual time from seconds of 5. Okay, that's the timeout. So let's run it and see how our application behaves. So back in our running application, let's just refresh it. So now the application is calling microservice, proxying on third-party joke API, and that's working. So if it responds within 5 seconds, we'll get the joke back, which we did there. But if it takes longer than 5 seconds, if that random time takes longer than 5 seconds, we'll get this. So what will happen is the client will just loop, and behind the client, the JSON that will be returned, which is our .NET microservice. If we keep refreshing it, boom. If it takes more than 5 seconds, we will get this timeout exception. So it's a way of short-circuiting the infinite wait that we had to start with, but it's not very granular. We're not catching that exception. We're not doing anything with it. So that's how to implement a timeout. So you're not getting that indefinite wait. You're actually constraining that wait to a particular time frame. So that's timeout. The next pattern I want to talk about is what I define as improved timeouts. So it's a timeout pattern that we've seen previously, where we determine when we stop waiting, but also we actually have more granularity inside the request. So let's have a look at that. So here we are back in our code. We'll actually get rid of the property for timeout and use a third-party library. So the third-party library, resiliency library we're going to use is Poly. So Poly is specific to .NET, but there are other libraries like resiliency for J that you can use for Java, and there's other ones for TypeScript. So we're just using Poly as an example. You can do this in any language. So first thing I want to do with Poly is define a policy. I then call timeout async. And it expects a timeout value. So we're still using 5 seconds as our timeout value. Then the bit that we want to do, we want to wrap that policy. And we want to execute a block of code asynchronously. So the block of code that we want to execute asynchronously is the block of code that is below there. So that is our client call to the third-party API. So I'm just going to move that code up into my async anonymous function. Boom. Format it a bit better, because we all love clean code. And that is that. And then I've got a cancellation token that I need to define, CT. So let's define cancellation token as a new cancellation token. So what this does, you can have control over the cancellation token itself. So you can cancel any async tasks that are within that execute async statement. So two that you can have control over are the get async from the HTTP client and the read async string. So if I redeploy this change to my application, and hit refresh, tell me another. Again, our timeout for this is 5 seconds. So if it returns within 5 seconds, we're fine. So they both returned fine. Let's go back to our site microservice, refresh that. Again, the third-party API is behaving. It's returning a result. Now we're waiting a bit longer. And there we go. So this is our timeout exception again. Now at this time, our timeout, we still have an unhandled exception. But what we can do with this sort of timeout is we can control via the cancellation token the particular calls. So give us more granularity into handling timeouts. So the next pattern we're going to talk about is graceful degradation. So this pattern is all about what to do when we have problems with our third-party API call. How do we handle and degrade it gracefully? And we do that by using a fallback. So let's see how we can implement a fallback inside our code. So here we are back inside our class, inside our controller of our .NET microservice. We're defining a fallback policy. Again, this is of type policy. And what we're going to do is this policy is going to return a IEnumerable, which is a list of jokes. And when's it going to execute? Well, it's going to execute when it catches an exception. So you can be quite less generic. This is quite generic. You can be quite targeted, but we're going, for purposes, we're going to use exception as the invocation point. Next, we define what that fallback action is. And what we're going to do is define an anonymous async inner function that will return us a new joke. So we need to make a list. So in .NET, you can make a list of size 1 in line. So I'm making a new joke. It has a setup, it has a punchline, and it has a source. So the source is going to be different for this because this is a fallback. So this is going to tell us where the joke has come from. So the setup is I'm in a band called 1023 MB. We haven't had any gigs yet. Kaboom. Tish. So the source for this is fallback. So that will enable us to see when we actually hit the fallback. Next, we're going to define a policy wrapper. So a policy wrapper is a way that we can set precedence over the policies that we've already defined. So inside the policy wrapper, we're going to define our fallback policy, which wraps our original policy. So that means that when the original policy, which is the timeout, which I've set, when that hits an exception, i.e. it waits more than 5 seconds, it will hit the fallback. So here we're back in our client, we're testing it out, we're refreshing. A third-party API worked. Refresh again, tell me another. And here we are. I'm in a band called 1023. Source is fallback. So what's happened is the timeout's happened, and the exception has been caught by the fallback, and we have returned the fallback. And that's what it looks like in a microservice. So that was a fallback in our API gracefully degraded. Next pattern I'm going to talk about are retries. So with the retry pattern, it is all about executing requests after a time. So you're retrying the API after a set time. So let's see what that looks like in code. We're going to keep our fallback policy, but we're going to add and change our original timeout async to 2 seconds instead of 5, just to speed things up a bit, and implement a retry policy. So defining the retry, it's a type policy, Again, we're going to handle exception. And we're going to retry async. So here we can define how many times we retry. We're going to define it as 5 times. And then we add the retry policy to our policy wrapper. So what this in effect does, it will retry 5 times. And if on the 5th retry we have an exception, it will push to the fallback. And just tidying that up a bit so you can read it a bit better. So let's F5 this, deploy it, and see how it works. So here's our client. We hit refresh. Now remember, we are every 2 seconds, we will time out. We will retry 5 times. And if we don't get anything, we will fall back. So again, we're hitting tell me another. Third-party API is coming within that time frame, so 10 seconds. So here we're loading, we're retrying. The APIs came back. We're loading, we're hitting the API, we're retrying, it's coming back. And again, it's coming back, which is always the way when you're trying to demonstrate something. We're trying, we're retrying, we're retrying. Every 2 seconds, if we hit 5 of these retries, then we should then hit the fallback. And there we are. So that's the fallback being invoked, and our client is still functioning, even though our API is throwing out a number of timeouts. Cool. So the next pattern that I'm going to show you is exponential back off. So exponential back off is an extension of the retry pattern. If you think of the retry pattern in its very essence, it is retrying an API, in our case 5 times. If you had many different clients all retrying that same API 5 times, you're actually building a very fine distributed denial of service attack on that API. So obviously you want a way of smoothing how often that API gets hit because you don't want to bring it down. And this is where exponential back off comes in. So how this works is we back off, so we increase the time between retries. So when our React web application hits our .NET microservice, proxies through a third-party API, then if we are waiting, it will retry after 2 seconds. If we don't get that doesn't work either, we will retry not after another 2 seconds, but after 4 seconds. And then the next retry won't happen until 8 seconds, and then the next retry won't happen until 16 seconds. And then hopefully by that time, we will have a response because the third-party API has recovered from whatever error it's having at the minute. So that's how the exponential back off works. So let's see how we can build that in code. So here we are back in our code. So the exponential back off, as I said, is an extension of the retry policy. So we go into our retry policy and we do a little change. Just tidy it up. And instead of retry async, we just want to be a bit clever. So here we wait and retry. And here, of course, we still define how often we retry, but we also define how often we wait between retries. So that's what I'm defining here. How many times we want to retry and how often we want to wait between these retries. So what we're going to do it exponentially. So we're going to define a little math to the power of 2 between retries. So that will give us our first retry be 2 seconds, second retry will be 4, and then 8. And then our final retry at 16. Just make sure I'm spelling it correctly. Picked it up. There we go. Okay, so now we've added that exponential back off to our retries. Tidy that up, format it nicely, and F5 and deploy it and see how that will work. So again, we will see the same behavior that we saw from the retry policy, but what we'll see is a longer wait between retries, and then eventually we'll see our fallback being invoked. So here we are, we're invoking, it's waiting, so it's at least trying at least once. We try 2 seconds, then 4 seconds later, and then 8 seconds, and then finally 16. If it doesn't get anything after 16, we'll have our fallback. This is taking a while. Will it be the 16 seconds? And there it is. So actually 16 second first time. That's our fallback. If we invoke the API again, tell me another. Are we trying 2 seconds? We're trying 4 seconds. We're trying 8 seconds. And this time the API is returned in time. And then we tell me another. So each time we are invoking the API. The first time we hit the fallback because our exponential back off was all invoked. And then subsequent times the third-party API returned in time. So the addition to the exponential back off is the next pattern I'm going to talk about, exponential back off with jitter. So as I mentioned earlier, with the retry pattern, we are creating a distributed denial service if we have enough clients retrying our API at a specific time. And with exponential back off, we're increasing that time between retries. But what inevitably happens is we all, when we're building out our clients, we all do that math.power2 and end up clustering our retries anyway, which really defeats the purpose of having that exponential back off in the first place. So a great addition to the exponential back off is adding a jitter. So what a jitter is in essence is a random amount of time in between the retries that the exponential back off is giving you. So it adds or subtracts an amount of milliseconds. So then distributes those calls over a greater time span and allows the API to recover when being called. If you want to know more about this particular pattern, there's a link there to our builders library where you can read a bit more in depth about the exponential back off with jitter pattern. So let's see how you can actually implement that in code. So here we are. Again, we'll go to our retry policy because this is an evolution of that again. And we want to change or add something to the time span. So we have our retry, we are, every retry attempt, we are exponentially increasing the time, but we also want to add a random amount of time. So we add, in this case, milliseconds, a couple of milliseconds, randomly to the end of the span that the exponential back off is calculating. And that way, we are randomizing the retries, which is an easy to implement, but is very powerful. So that's the exponential back off with jitter implemented in code. The next pattern, in pattern 5, is called the circuit breaker. So all of our patterns, as they've evolved, you've seen that we're trying to reduce the load on the third-party API. We want to give it time to recover. So the circuit breaker pattern is specifically aimed at doing that. It, instead of waiting between retries, it actually circuit breaks any calls to that API itself. Let's see what that looks like. So we have a request proxied through our .NET microservice. It's our third-party API, which is not very happy. So it's timing out, we're retrying, we're not getting a result. So what the circuit breaker does, it actually implements a block to calling the API. So now when the .NET microservice makes a call to the third-party API, it hits the circuit breaker instead, doesn't go anywhere near the third-party API, and returns another fallback. So that way, our clients can still operate even though the third-party API is not being hit. Then, after a number of minutes, the circuit breaker will lapse, and we can again start hitting our third-party API. But hopefully by then, it'll have recovered from whatever fault it's currently having. So let's see what that looks like in code. So for the circuit breaker policy, we just need to define a new policy. So I'm going to do that underneath the retry policy. I'm going to call it circuit breaker policy, very imaginatively. It's another policy type. Again, we need to handle it on exception, so it'll be executed on exception. And we define the circuit breaker async. So let's just tidy that up and define what's it going to do. So it's going to allow us 5 exceptions from our third-party API before implementing its circuit breaker. And then how long is the circuit breaker going to be implemented for? I'm going to set that to 1 minute. So that's our circuit breaker policy. But now, what we're going to do when it's in effect. When the circuit breaker policy is in effect, so that 1 minute, we need to do something. So I'm going to define a fallback policy for that circuit breaker. Now this time, I still want to return an enumerable of joke, but instead of handling exception, we need to handle a specific type of exception, because we only want this to be called when our circuit breaker is invoked. So we handle the broken circuit exception, which tells us that yes, the circuit breaker is in effect. So when that's in effect, we define our fallback, which is very similar to our other fallback that we implemented during the Graceful Degradation pattern, i.e. we're defining a new joke, or a new list of jokes of size 1. So here is the new joke, just format that correctly. If you remember, we've got a new joke. The joke type has a setup, has a punchline, and the source. So why did the developer go broke? Because they used up all their cache. Kaboom tish. Sorry for the jokes, but that's just the way it is. So this time we've set the source as circuit breaker fallback, and we just add it to the policy wrapper. So again, order of precedence, we want that circuit breaker fallback, and then we want the actual policy that invokes it, which is the circuit breaker policy. So once we've finished that, tidy it up a bit. There we go. And so, yep, that's all right. And then we deploy. And so if we're deploying, tell me another, let's see. So we want, when we get 5 invalid calls from the API, our circuit breaker is going to be in effect. So that's going to take 10 seconds, so 5 times 2, because remember our timeout happens after 2 seconds. So tell me another. So now we're retrying. The API is not responding. We're retrying. We're getting that exception. And then when we get that circuit breaker exception, or the circuit broke exception, then we'll get our circuit breaker fallback. So this is taking a while. Hopefully we'll get that fallback now. Yep, and there we are. Why did the developer go broke? And that's our circuit breaker source. So our circuit breaker is invoked, and now every time you go tell me another, it will get we will get the circuit breaker, and that will be the same for the next minute. And then after that, we'll start hitting our third-party API again. So that's the circuit breaker. So that's our 4 patterns, 5 patterns, I should say, to help you build more resilient apps. And I want to end on one practice, which is chaos engineering. So what is chaos engineering? So chaos engineering is a practice where you stress, observe, and improve. So you stress your application, you see what happens, and then you use those observations to improve that application over time. So this allows us to improve the resiliency of our app. So what we've been doing with our little third-party joke API and microservice is improve the resiliency so that the client can keep working. We can also uncover hidden issues. So we've seen a number of issues that we highlighted in our previous app. If the third-party API has issues, then we have made that application more resilient. It also exposes blind spots, so we can add specific observability and monitoring to those blind spots, so we can then know when things have happened, and a lot more besides. So last year at reInvent, we released the Fault Injection Simulator. I'm just going to demo this quickly for you by creating what we call an experiment. So the way the Fault Injection Simulator works, we create an experiment that does things to your infrastructure. So in this experiment, I'm going to simulate my third-party API going down for a minute. What I do, I create a name for this experiment. I give it an action, which is going to be stop instances. A very nice description. I'll stop my API instances. And the action type. So that again is stop instances. And then I need to target specific instances. So here I'm saying all these instances will stop for 1 minute. So my third-party API is running on these instances. So next I need to identify them. So it's quite granular in what I can actually stop and start. And I'm defining that tag that defines my instances. Once that's done, I can save this experiment, and it'll prompt you with a warning, because what you're doing is actually going to stop real things, real instances. There's no simulation here. It actually will happen. So if I then run this experiment, again, I'll get that warning to go, these instances will really stop, and then execute. So that experiment will then spin up. So at the minute it's pending, and it hasn't started yet. So if I go back to my instances, they're still running. So then if I jump back into the Fault Injection Simulator, you'll see it's still pending. So if I refresh, it's now running. So as it's running, I should expect my APIs to go down, and there they are. So they're now stopping. So it's now stopping my API servers, and they will be down for a minute. So as well as stop instances, there's other actions you can do with the Fault Injection Simulator. Some of them are listed here. You can see that they're quite specific things you can do. So the thing about the Fault Injection Simulator and chaos engineering, you need to be targeted about what services you want to inject a fault into, at what time of day you want to inject that fault, so you allow them to recover, and so you don't impact your application. So a minute has gone past, and so what's happened to my instances? So now if I refresh, they have now started up again. You can see my experiment is completed, and now I'm able to, the application will continue running. So in that minute, I would observe the application and see what happened when I brought down the API servers. So that's the talk for today. We went through 5 patterns of timeouts, graceful degradation, retries, exponential back offs, and circuit breakers, and I've showed you one practice, all to help you build more resilient applications and keep your users happy in using those applications. Thanks for staying to the end. My Twitter handle is here. Please reach out if you have any questions on building on AWS. Until next time, bye.